So we're now ready to talk about the structure and functionality of the Java ConditionObject class. And this particular class is quite interesting for a variety of reasons. One reason is because how it works and what its semantics are. Another reason is for how it's actually integrated into other parts of the Java class library. And you'll see as we look through this in more detail that it's kind of put in an interesting place. So a condition object provides the Java implementation of a condition variable. So we've talked about what a condition variable was before, which is basically a synchronizer that can be used to have a thread put itself at bay or keep itself at bay until conditions involving shared mutable state change to its liking, or may change to its liking, as we've seen. As you can see, condition object implements the condition interface, and I strongly recommend you read the condition interface, which has lots of good stuff explaining what the methods do. And it does a really nice job of giving you the essence of what this particular abstraction is about. A condition object is actually nested within the abstract queued synchronizer class. So if you recall, the abstract queued synchronizer is this framework that's used by Java synchronizers that need various kinds of FIFO wait queues to have threads park themselves waiting to be notified to wake up and do something. And in this particular case, as you can see, condition object is basically a nested class within abstract queued synchronizer. Now, the good news is you don't really have to know or care about this because you rarely, if ever, probably never, actually make an instance of a condition object directly. But instead, you use a factor method that's defined on the lock interface in order to create the corresponding condition object that's associated with that lock. The condition object implementation also has something called a node, and the node is used to implement a wait queue that will be used to allow multiple threads to wait for the condition that they're waiting on to be satisfied. So you can see here it's kind of nested like the Russian dolls. You have abstract queued synchronizer, which has condition object nested inside of it. And then there's a bunch of nodes that keep basically a linked list or a doubly linked list of condition objects that correspond to the threads that are waiting to have their conditions satisfied. So this allows the wait set, which is what that set of threads is called, to coordinate their interaction. And they basically are just going to park there waiting their turn. And the wait set and the conditions are used, the condition objects are used to select the order and the conditions under which a given thread that's in the wait set will get its chance to go. In other words, when it will no longer be kept at bay or no longer will keep itself at bay to be able to make forward progress. As we've talked about a number of times before, condition objects are always used with a lock. And we'll see an example of this very shortly when we talk about the array blocking queue implementation. So there's always a lock, typically a reentrant lock, that's associated with the condition object. And this lock is used to protect the shared state in a condition expression from being corrupted during concurrent manipulation. So in other words, if multiple threads are sharing some mutable state, then this lock is used to protect the state so we don't end up with corruption and race conditions that would otherwise occur if multiple threads were reading and writing or reading and reading and writing and writing and so on to the values in the shared mutable state. As I mentioned just a little bit ago, the new condition factor method is defined on the lock interface, thus on the reentrant lock implementation of said interface, and that's used to return a condition object that will be associated with that particular lock. So we think about the new condition as returning a condition object that's associated with the reentrant lock or the lock that called the new condition factor method. Both reentrant lock instances and condition object instances have internal queues, and those are separate queues, and they're used for somewhat different purposes. So you can see here, we kind of show the queues for each of the different types of locks. The reentrant lock uses a queue to basically have threads park themselves that are waiting to acquire the lock. So that's where they're going to go and suspend themselves and become dormant when the lock is being used by some other thread. And that thread will typically hold that lock for a hopefully fairly short period of time. Condition objects also have a queue. Each condition object has a queue, and that's used to queue up threads that are waiting for some condition or conditions to become true. And these conditions may block for a longer period of time. The locks typically don't get held for very long, but the conditions may take a while because, of course, it all depends on how quickly the state that's shared is changed to correspond to the new behavior that some thread may be waiting for. For example, if you're waiting for a queue to become not empty, if that's the condition you're waiting for, and it takes a long time for that to happen, well, you'll just keep being parked in that particular queue, and you'll be part of the wait set for a while. User-defined condition objects, or rather user-defined objects, can have multiple condition objects. And this is very important. And when we take a look at the array blocking queue example here shortly, you'll see that it actually has a pair of condition objects, one that's called not empty, which is used to have threads wait while the array blocking queue has got nothing in it. And then another one called not full, which is used for threads that are trying to put things into a queue that's full. The ability to have multiple condition objects in user-defined Java objects is the real reason why they define condition objects, because there already was a single condition object part of a Java object, but that turned out to be too limited for reasons we'll talk about later. So the ability to have multiple condition objects enables more sophisticated and much more efficient ways to coordinate multiple threads than what you get out of the box with classic Java. And the reason for this is you can have multiple wait sets per user object that share a lock and are notified on different conditions, such as the queue being not empty, such as the queue being not full. In contrast, Java's built-in monitor object only supports a single monitor object, one and only one monitor condition. And in particular, there's just a single wait queue for a classic Java object, which is why they had to go ahead and build these extra features into the Java class library in later versions of Java to support the more sophisticated use cases. And we'll talk about Java built-in monitor objects and monitor locks and monitor conditions more when we get further along. The reason why the default behavior of Java built-in monitor objects is so problematic is you end up with very inefficient programs that require an excessive number of notifications and the use of a method called notify all. And the reason for that is you end up basically requiring both producer and consumer threads to wake up on every change to the queue, even if there's no possible way they could make any progress. And we'll talk about that later. And if you want to get a little preview of coming attractions, take a look at the link at the bottom of the slide, which explains the downside of having this. So that's the end of our overview of the structure and functionality of Java Condition Object. As you can see, there's a lot to it, and it's a little subtle how it gets used. And we'll cover this in more detail when we talk about the key methods in an upcoming lesson, as well as some good examples from the Java array blocking queue implementation that we'll look at next.